Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Today we'll finish setting up the geometry pass stage of the graphics renderer. We are also going to deal with resource states and barriers by writing some new helpers and using them to set transition barriers for geometry pass buffers. Continuing the implementation of the geometry passes render function, we can set the primitive topology to a triangle list since we are going to render a single full screen triangle. Then we call drawInstance function. Calling this function without setting a vertex buffer will result in the specified number of vertex shader invocations. In this case, the full screen triangle's vertex shader that we used in the pipeline state object will be called 3 times. I'll come back to how this triangle is generated in the next episode. Since we created a root signature with one 32-bit root constant, we can use it to send the frame number to the pixel shader. Remember, this is still scratch code so that we can set up and test the gpass submodule. In reality, I would pretty much never use a static variable like I'm doing here. Next, we need to tell direct3d where our pixel shader should write its output. In other words, we need to specify a render target. That's of course why we have a main buffer and depth buffer, so we can use the depth buffer for the depth prepass and the main buffer for the render pass. We can add 2 functions to do exactly that. In the depth prepass, we don't have any color output, so we only need to set the depth buffer as our z buffer. First, we get the depth stencil view of the depth buffer, and then we call clear depth stencil view with this descriptor and the clear value for depth and stencil to clear the buffer. Since all 32 bits of the pixels are used for depth information, we can tell the API to clear both depth and stencil bits of the pixels by setting the flags accordingly. Finally, we set the render target for output merger by calling omSetRenderTargets function. Note that we don't set any render targets, but only a depth stencil buffer. For the render part of geometry pass, we need to set the main buffer as the render target. Therefore, we get the render target view for the first MIP level of main buffer. Eventually, we will also read from the depth buffer during this render pass. That's why we also attach the depth stencil view, which contains depth information from depth prepass. Next, we clear the render target view using the clear value, and this time we call omSetRenderTargets with both a render target view and a depth stencil view. So now we have defined all functions that we need for doing the gpass. Let's call them in a render function in core CPP. First, we need to make sure that the gpass buffers are big enough to contain the largest of our windows. Therefore, we call setSize every frame for the surface that's being rendered. Remember that gpass functions expect a D3D12 frame info structure that describes the scene that we are trying to render. We need to define this structure first. Let's add it to core header. By the way, we don't need to forward declare descriptor heap anymore since resource header is now included in common headers. Right now, the only data that we need in D3D12 frame info are the dimensions of the surface. So I'll add a width and a height member variable. Now we can have an instance of this frame info in the render function and use it everywhere it is needed. Next, we bind the viewport and scissor rectangle to the rasterizer stage. This determines the portion of the render target that is used for outputting pixels. Obviously, we want to render to a region of the main buffer that is as big as the dimensions of the current surface. That's why we use the surfaces viewport and scissor rectangle here. Although we don't have any code for depth prepass, we still can clear and set the render targets and call the empty function with the command list and frame info. Moving on to the geometry and lighting pass, we can again clear and set the render targets and call the render function of gpass module. This was the last step in geometry pass, which will be followed by post-processing step. So let's run the application and see what happens. We get an error here saying something about a resource not being in the expected state. I think I need to do some explaining here. Imagine we want to use the depth information from a scene to determine which lights affect what parts of the world that is viewed by the camera. First, we generate the depth image of the scene using a depth-only pass. This will write the depth values of all rasterized pixels to the Z buffer. Next, we want to read this information in a compute shader to calculate light intersections with the objects in the scene. Because in general not every object is lit by every light in the scene, this greatly reduces the work that needs to be done to determine the color of each pixel. Obviously, we only want to read from this buffer when depth pass has finished writing depth values. But how do we know when the buffer is ready for reading? Here is where resource barriers come in. Before DirectX 12, setting barriers was the responsibility of the driver. Although drivers often did an excellent job of applying barriers, there was always some extra overhead because it's rather difficult, if not impossible, to know the exact render path of a program. DirectX 12's barriers are intended to diminish this overhead by putting the responsibility of placing them in the hands of the developer. In order to do that effectively, developers now have to know a lot of nuances about barriers and resource states. That's why it's really important to read the documentation and everything else from sources who know what they are talking about. As the title of this presentation indicates, this is an oversimplified discussion of barriers and resource states. You're encouraged to read more about this subject, since it plays an important role in rendering using DirectX 12 API. So what do barriers do? Well, conceptually, you can think of a barrier as something that ensures that a resource is in a correct state before it's accessed for the intended usage. In the example of depth pass and light culling, the barrier prevents reading from the buffer resource while it's still being written to. Again, in reality, there is much more going on. For instance, the memory layout of the resource could change to optimize access for different usages, or even the entire pipeline could get flushed. There are three types of barriers. The barrier in the former example is a transition barrier, which, as the name indicates, transitions a resource from one state to another. As I mentioned in the video about texture resources, each resource is placed or mapped onto a region in a D3D12 heap. Most of the time we use committed resources, which implicitly create a heap and map the resource to that heap. However, it's also possible to create a heap explicitly and place the resource in that heap. These are called placed resources. It's possible to place multiple resources in the same heap and even map them to the same region in the heap. For example, we could have an RGB texture resource as a render target and another texture resource that contains normal information of the scene and map it to the same offset in the heap. As long as we are not using those resources at the same time, we could alternate between them using an aliasing barrier. Another example is using aliasing barriers for streaming texture data using tiled textures and reserved resources. The last type of barrier is the UAV barrier, which synchronizes reading from and writing to unordered access resources. So to wrap this up, remember that using barriers has performance implications. To use them effectively, read the documentation and other good resources. Use barriers only when needed, which is also described in the documentation. Apply barriers together when you can. That way, the GPU has more information in order to do optimizations. Use split barriers. A split barrier consists of a hint to the GPU that a resource is about to be transitioned before really setting the barrier. I'm going to get fancy and use split barriers in the next episode, so subscribe to the channel to stay tuned and get notified when that video is out. There is an excellent resource on various graphics programming topics, which is a blog written by Matt Petinio, if I pronounce it correctly, sorry otherwise, who is currently working at Ready at Dawn Studios. His blog articles have been a goldmine for me over the years, and I can't recommend reading them enough. It's also a fun coincidence that right when I was working on shader compilation videos, Matt wrote 3 articles about shader compilation. I just found out about these and still need to read them though. Anyway, if you'd like to read an in-depth discussion of barriers and resource states, this 6-part blog post is the place to go to. I couldn't find any other resources that would explain it as detailed and were as well written as these articles. There are even animated slides so you can play the sequences and really understand what's happening. Thank you, Matt, for sharing your knowledge with us. Before going bananas with barriers, let's get our feet wet by writing a little function first that can help us with setting resource transition barriers. I'll declare this function in helpers header and implement it in the helpers CPP file. Setting a barrier is a command that we can record using a command list. We also need to know which resource needs transitioning, along with its before and after states. Optionally, we could also set barrier flags and specify which sub-resource we would like to transition. For example, if we had a texture with multiple MIP levels, we could use this function to transition just one of those MIP levels. The default is to transition all sub-resources at the same time. In the implementation, we simply fill in a D3D12 resource barrier structure. Because this function is specifically for resource transitions, we need to choose the right barrier type. We can fill in the rest of data members using this function's parameters. It's common for direct 3D structures to use a union of different structures. This is the case here as well. When we specify the barrier type, we need to fill in the corresponding structure in the union. In this case, it's transition structure that we need. Finally, we add a resource barrier using this data. Let's take this function for a spin and use it to transition the current back buffer from render target state to present state. Looking at our render function, we know that post-processing will write the final image onto the current back buffer. Therefore, the current back buffer state should transition from present to render target. After post-process, when we would like to present the current back buffer, we need to change the state from render target back to present. Although we only had just one resource barrier here, often we'll need to set multiple barriers. It's also recommended to group barriers and set them together, so the driver and GPU have more information for optimizing execution of tasks. Our helper function here can only set one transition barrier, so let's create a helper class which enables us to set a group of barriers. Here I define an array of 32 resource barriers. It's a rather arbitrary number, but it's pretty hard for me to imagine a render path that requires more barriers before needing to apply them. We also have an offset variable that advances every time a barrier is added to this array. Now we can write functions that add different types of barriers to the array. The first one adds a resource transition barrier, like the one we just wrote. It takes the same parameters, so I'll copy and paste them here. We make sure that we have a valid resource and that there is space left in the array for one more barrier. Then we fill in a D3-D12 resource barrier structure like we did before, but now instead of having a local variable, we take a reference to the next available slot in the barriers array and write to it. We also need to advance the offset. The next function adds a UAV barrier. It's pretty much the same, except now we fill in the UAV structure in the union and specify the barrier type to be UAV. In this case, we only need to specify the resource and optionally the barrier flags. The final barrier function is one that adds an aliasing barrier. Here we need the before and after resources. The next function applies all barriers in the array at once. First, we make sure that the array is not empty. Then we set the barriers by calling resource barriers using our barriers array, and finally we reset the offset, so we can reuse the array. Now we can use this helper class to group our barriers and submit them at the same time. First, we add an instance in core CPP. Then we use it in the render function to add and apply the barriers. Instead of calling the helper functions from this class directly in the render function, I'll write functions for the submodules that need the barriers. For example, to get rid of the resource state error that we got earlier, we need to set transition barriers for the main and depth buffers in gpass submodule. Here I add the functions for setting the barriers. We have one for depth prepass step, another one for gpass render step, and finally one for post-process step. In depth prepass, we want to be able to write to the depth buffer. So we need to transition it from read state to write state. Remember, we created the depth buffer with an initial state that was depth read, pixel shader resource, and non-pixel shader resource. So we need to transition from this state to write state. In gpass render, we want to read from the depth buffer and write to the main buffer in a pixel shader. So main buffer is transitioned from pixel shader resource state to render target state, and the depth buffer from write state back to its initial read state. In post-process, we read from main buffer in a pixel shader, so it transitions from render target state to pixel shader resource state. Going back to the render function, now we can add the barriers for each step and apply them just before the resources are accessed. A quick fix for this assertion here, and we can launch the application. Something something back buffer something something present. Let's move this present call to the end of the function and see if that helps. It didn't help. I don't exactly know what's happening here, but I think execute command lists and present are out of sync here. So let's put the call to present right after we call execute command lists, but before signaling the fence. Awesome, it worked. Okay, last bug for today, I hope. Here, the descriptor heap allocator is kindly letting us know that not all descriptors were freed when we closed the application. I know the only new descriptors that we added today were the ones for gpass buffers. So let's investigate. In shutdown function, I'm releasing the buffers, so that looks good. Another place where we release the buffers is in create buffers function, which is called when the buffers are resized. Since we have differently sized windows, the buffers got resized, and here I see I made a typo and called resource instead of release function. Fixing that typo got rid of the problem. That's it for today. Next time I'll continue with post-processing. Thanks for joining me, and I'll see you next time. Bye. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!